compound interest. So we've been discussing exponential functions. They are functions that have the variable in the exponent. And so let's take a look at a real-life example of a function that has a variable in the exponent, and that function will be the compound interest function or formula. So we want to use compound interest formulas to determine the total amount in an account after a given number of years. Well, we know what an exponential function is. Any function of the form f of x equals b to the x, where the base is positive but not equal to 1, and the exponent x is any real number. Okay, so b is the base, and in an exponential function, the exponent is in the variable is in the exponent. Okay, so as I mentioned, compound interest formulas are examples of exponential functions. In other words, you have variables in your exponent. Okay, we have two formulas for compound interest. And those of you who have done a little science may recognize the second one. If you have n compounding periods per year, for example, you're compounding monthly, so you have 12 compounding periods. The formula is A is equal to P times the sum of 1 plus R over N, all that raised to the NT. If you have continuous compounding, and again, you may have seen continuous compounding if you've done some science work, it tends to pop up there fairly often. The formula is A is equal to P times E, which we know is a natural base, raised to the R times T. Well, what do these letters stand for? A is the ending amount, often called the annuity, okay? P is the beginning amount, called the principal. R is the rate, and the rate is in decimal form, and T is the length of time in years. So the ending amount in the first formula here is equal to the beginning amount times 1 plus the rate divided by the number of compounding periods per year, and that sum is raised to the number of compounding periods per year times the number of years. Okay, so those are our two formulas we're going to use. And again, notice I have variables in the exponent. This is why they are exponential functions or exponential formulas. All right, let's make use of those. Keep it simple, and we're going to make use of our calculator. Example 1 here, we're just going to do one. You're going to invest $8,000 for 6 years, and you have the choice between two accounts. The first account pays 1.2% per year. It's compounded monthly. The second pays 1.19% per year. It's compounded continuously all the time. Which is the better investment? Which one gives you the most money 6 years later? Okay, so let's do these two. The first one is 1.20%, and the compounding is monthly. Okay, this formula number 2 is for continuous compounding. So we're going to look at formula number 1 because we're compounding 12 times per year. Monthly means every month, and there are 12 months in a year. So A is equal to the ending amount is equal to the beginning amount times 1 plus the rate over the number of compounds per year, raised to the number of compound periods per year times the number of years. So A is equal to, we're investing $8,000, so that's our beginning amount. 1 plus the rate as a decimal, 1.20 as a decimal is 0.012, divided by the number of compounding periods per year. We're compounding monthly, so that's going to be 12, raised to the n, which again is 12, times t, 6 years. T is number of years. This goes into a calculator. and out comes 8,000, if I did my math right, $596.93. So this account, if you give them $8,000 for 6 years, paying 1.2% compounded monthly, in 6 years you will have just about $8,600. Okay? The second account, it's paying 1.19%, but it's compounding continuously. Okay, that's our second account. A little less in the rate, but it's compounding all the time. It's nonstop compounding as opposed to once a month. This account makes use of a continuous compounding formula, which is a little simpler. It's A is equal to P times the natural number E raised to the RT. So our amount is our beginning amount, our ending amount is our beginning amount of $8,000 times E raised to the R times T. Well, the rate is 1.19% as a decimal. That's 0.0019. I think that's right. 1.19, no, just 10. Yes, just 10. Sorry about that. Too many zeros in there. Move the decimal to 0.119. That's better. And the number of years is 6. Okay, and just in case, I'm going to pull out my calculator because I may have made a mistake and I want to double check. So I can do this with you. Okay, let's go to get out of my graphing. Okay, so 8,000 times E raised to the, well, the E exponent button, I'll show you here. If you want, you can use the E button is here, it's a blue, right there. So you can use E and then use this for the exponent. But there's also an E to the exponent right here, a blue, that uses the blue function of the natural log we'll talk about later. So let's use this E to the X. So blue key, E to the X. I got an E, whoops, you can't see that. I got an E raised to the power, and my exponent's going to be 0.0119 times 6. And out came $8,592.09 when I round this to the nearest penny. That's 9 cents. And so which is the better investment? Well, it looks like the first account, which was a little higher but compounded less frequently, is about $4 better, maybe $5. So the 1.2% compounded monthly account is the better investment by about, this is almost 97, that's almost 92, by about $5. Not a big deal. You can't see that, not a big deal, but it's just a little bit better. So compound interest is a function or a formula that has variables in the exponent, and therefore it is an exponential function.